Hello everyone, this is Renjie. Today is our final day on our Python exercises. We are going to introduce a very important library called NumPy in this tutorial. We have used NumPy library in previous tutorials. If you remember, in day 4, we called NumPy several times to induce the cosine function. But today we are going to give a short introduction of what is NumPy, how can we use NumPy to solve engineering problems. Remember that NumPy is a very big library, so we are going just to touch a little bit of NumPy. And if you want to use other functionalities of NumPy, in addition to the material we are going to cover today, you are welcome to use internet or go to NumPy official website to get more information. So we split today's class into two parts. In part 1, we gave a short introduction of NumPy library and working majorly on 1D arrays. So we'll teach you how to represent things using NumPy and how to use basic elementary numerical operations of NumPy. At the end, we will demonstrate that NumPy is very efficient compared to what we can write in native Python. In part 2, we are going to review some basic linear algebra operations. Then we are going to use NumPy to perform these linear algebra operations in a very fast way. Let's get started. As I always say, after you opening this file, you need to save it to your own drive by clicking this button. So let's click it to create a copy, then open a new tab. So what is NumPy? NumPy is the most widely used Python library for numerical computations. So for us engineers, we deal with numbers, we do all these numerical computations. So NumPy is a must-known for us engineers if we want to use Python to solve engineering problems. And another library called SciPy, which is you can view this as a extension of NumPy, and it has some more specialized data structure, and combined with NumPy, SciPy and NumPy can help us to deal with almost all the basic engineering problems. So you may ask that why do we need to use NumPy? Because as we introduced before, Python has its own mathematical operations, and it can also represent all these numbers either by integer or by float. Why do we need this NumPy? This is because, as you might know, that math is pretty complex and there are lots of functions to do when you do numerical analysis. If there's no NumPy, you can write your own equations or formulas using native Python environment, but that means that you have to develop the function and test it. And you also need to make sure that this function is optimized so the computation time is fast. But using NumPy, we can solve all these problems. First, that NumPy is developed by a lot of people, and it contains a lot of functions that can be used to help us to do a numerical analysis of engineering problems. The other very important thing is that NumPy functions are highly optimized, and which means that the execution time for NumPy function is much shorter than what we can get by writing a native Python function. So let's start with importing NumPy. So simply import NumPy as np. Again, SNP means that we want to have a shorthand notation for NumPy, so it's easier for us to type. NumPy is used to represent numerical values, so it is represented by numerical arrays. So how can we represent things in NumPy? So we can use this notation. So NP array means that we want a NumPy array. Then that's a list. That's basically the elementary Python environment list. So in this way, remember the typecast or type conversion we covered in day 3. So in this way, we convert this list into our NumPy array. Let's do this. Then after the conversion, we have a NumPy array. Then same as the native Python list, we can know the length of this NumPy array. So let's do that. So we're calling the length function and act that function on the NumPy array we just created. Then that is 5. So because we have 5 elements, so that matches our expectation. And here is one thing that NumPy array different from the Python list is that because we are dealing with a mathematical object now, so we can have a shape for this array. So in this case, it's 5. So the shape is 5. So it's a 1D array. So there is another thing. For the on the other part of this tutorial, we are going to deal with 2D array. In that case, we are going to have a tuple. We can also change the entries inside this array by calling this simple index notations. So this is basically same as native Python list. So let's do this. We can NumPy provides some very useful functions for us to create arrays with certain properties. For example, we can call the NumPy ones to create a array with only ones with a certain length. So in this way, let's execute this. We want to create an array with length 5 that every element is 1. Similarly, we can create zeros. And the other benefit is that we can use the random parts. So it's NumPy library, there's a random parts. So we can use these random parts to create random variables. So it's basically the same as the previous notation. So we want to have a random value array with length 6. So by calling this function, we create this array. And if we call it again, the number changes because we want a random array. We can also fill anything into a list. So we want to fill 3 into x, then x is filled by 3. Yeah, this x is from the previous one. So we create an array with these 5 elements here, but now we want to change things and we fill it by 3. So the x is the elements from the old x is removed and changed by 3 by calling this x.fill function. There are some very useful functions we can use to create an array. First is arange. So arange gives us a range of arrays. So it's from 0 to this number. This is very useful when we want to make plots because for x-axis, most of times it's just a range of numbers. So instead of typing it by hands, you can just call this function to produce this array, this range array for you in one line. If you want to change the base from 0 maybe to another number by 2, and you want to change the increment, which in default is 1, to another number, in this case 0.5, we can just give it here. So it's lower end, upper end, and increment. By calling this function, we make the starting point to be 2, and we increase by 0.5, and we reach until it's smaller than 6. So it's bigger or equal than 2, but smaller than 6. So same here. So it's all the numbers smaller than 6, starting from 0 with increment 1. Similarly, we can use line space. So in line space, we just need to give it the lower bounds, the upper bounds, and number of elements we want inside this range. So in this way, we don't need to give it to compute for the increment. It will be automatically computed. So in this case, we want 6 elements inside the range 0 to 100. And because it's 6 elements, so it's 5 times increment. So it's 100 over 5, so it's 20. Again, these two functions are useful when you want to do plotting. Now we learn how to represent data in NumPy. So let's see how can we use this representation to do array arithmetics, because that's the thing we want to have, and how to use all these NumPy functions to perform different math operations. So NumPy supports common arithmetic operations such as addition, dividing, multiplication. So when you want, if you want to have to add 2 arrays, you simply need to call x plus y, and all the elements will be added here. So it will automatically perform addition for each element inside this array. So instead of calling a for loop to add it one by yourself, you can just use NumPy representations and add them together. So in this way, NumPy is much simpler than what you will do if you're using a basic Python representation. We can also multiply things using NumPy, and in this way, again, this multiplication is applied on elements inside, on every element inside this array. And raising components is same, so the notation is same as the Python notation, but when you perform these math operations on a NumPy array, it will be performed inside the array for each element. That's the key point you want to take from NumPy representation. In this way, we can do the raising power. Then we can call NumPy functions. So in this way, we want to first have an array of this. Then we want to compute the sign for each. So one way to do that is to use a for loop. Then you compute everything. But additionally, we can use similar notation as we did before here. So if you call a simple NumPy function and perform it on a NumPy array, this function will be automatically mapped to each individual of this array. So let's do this. So in this way, we are going to have the same answer as the previous one with for loop, but this line is we only need 1 line of code, but here we need 4 lines of codes. And as we will see later, using this vectorized operation is much faster than the previous one. We can also do some linear algebra operations. So we can do dot product. Basically, you represent things by a NumPy array. Then the first thing you can do is, as you can just use the dot product equation as shown here. then you just use a for loop to type them together. That's the old way of doing that. But with NumPy, there is a built-in function you can call, which is just dot. So you call NumPy dot then xy. In this time, it will do the similar thing here, but in a vectorized way. So the computation time is faster, and it's also easier to write. So you don't need to write the dot product by yourself. Everything is handled by NumPy. As I mentioned here and before, if we call these native NumPy operations, all the things will be performed in a vectorized way, which means that we are going to map this function into each element of this array. And because of computer architecture, in this way, computation is much faster if you compare to using a for loop. So we are going to demonstrate that by compute the norm of a very long vector. So first thing we are going to do is to actually construct this vector. So we construct NumPy array with 10 million random variables, and because we are using this NumPy function, then the type we created is a NumPy ND array. Then let's compute this with, because this we are going to compute the norm, so we first we write down this equation using our own defined function. So it's a for loop, then we times these elements together and take a square root at the end. Let's time this. This is relatively slow because we wait for like 3.2 seconds. So the total time for running this function is 3.2 seconds. Then we can perform the same operation. This time we're using NumPy dot. So this is a vectorized NumPy function. So we are going to measure the speed using this function. This time it's much faster. As you can see, it's only cost 15.5 milliseconds. So compared to the previous one, if you use a native NumPy function, it is much faster because everything is vectorized and other computer science people have taken care of how to optimize this function. So all you need to do is to perform this operation, and you don't need to worry about how these things is implemented. That's a major takeaway from NumPy. That's all for our first part of this tutorial. So let's review it. So we introduced what is NumPy, the motivation of NumPy, then we gave examples on how to represent things in NumPy 1D, and how to call NumPy functions, and NumPy functions normally are much faster than what we can write in Python. In the second part of this tutorial, we are going to deal with two-dimensional arrays. So two-dimensional arrays are very useful for arranging data in many engineering applications, and two-dimensional array normally represented as a matrix. As you can see here, to write down this matrix using NumPy, we just group all the rows into a big list, and inside this list, each row is represented by another list. So in this way, we have two lists. There's big one, and inside this big one, we have two small lists representing the row. So for these matrices, we have two rows. Each row has three elements. So we create one big list and write down two rows, and using np.array to let computer know that this is a NumPy 2D array. Let's do this. Then we can check the length of this array. So we can do length of A. So it's length of A. So the length for a matrix, NumPy 2D matrix, is number of rows inside it. And we also want to see the number of columns and rows. So the shape of this matrix, how do we do that? We just use A shape. So A is still this matrix. Shape is one of its property. So the property of this A matrix, the shape property of this A matrix is 2, 3. It's a tuple. To split this tuple, we can use, like we just mentioned in our first part of the lecture, we use the index notation to index the tuple. So the rows is just the first element, columns is the second element. Then in this way, number of rows is 2, number of columns is 3. We can also index this matrix using 2 indices. So this is very intuitive and corresponding to our mathematical notation. So it's A, then its first index is the row number of A, and the second index is the column index of A. For example, if we want to do 0, 2, then it's a row 0, column 2, and maybe we want to do 0, 1, so it's row 0, column 1. So let's print it. So it's 9.1 and 3.7. 9.1, 3.7. We can also directly access to each row by using a 1 index notation. So in this way, we are going to get the row number, the row elements of these matrices. We want to take a transpose of a matrix. To do that, NumPy gives us a very efficient function, and it is np.transpose. So you transpose this matrix A, and then we store the value as A transpose. The transpose of A is same as here. We can also do matrix operations. We can do matrix multiplications, and we can also using matrix multiplications to solve a linear system, either by inversion or matrix inversion or by iterative approaches. So let's first doing a matrix multiplication. So we have this matrix A. Let's represent this as np.array. Then we have 2 rows. So first row is 3, 2. Second row is 1, 4. Then x is just np array. Then it's 2, okay, 1. It's printed. Now let's verify the shape. The shape should be A is 2, 2, and x is 2. It's just a one-dimensional matrix. Then we can compute them together by using dot product. So you use A dot x. So in this way, we are telling the computer that we want to do matrix multiplication instead of elementary multiplication. So by calling dot product, we specifically doing dot product with matrix A at vector x. So the result is here. We can also times 2 matrix. So in this case, maybe we want a B, then B maybe can be another 2 by 2 matrix as shown here. Then we can do A dot B, and it's the same as here, but in this case we'll multiply 2 2D matrix. Here's the result. We can also inverse the matrix by calling the inverse function from the linear algebra module. So this is numpy module or numpy library, and inside this library we have a linear algebra module or linear algebra components, and inside these components we have an inverse function, which is just inverse, and we can use it to inverse A, and again we can use the same module, linear algebra module, and within this module we have a determinant, which is a det. So we use this function to compute the determinant of the matrix. In addition to dot product, there is another very important vector calculus we have, which is cross product. So you use cross product to get the vector that is perpendicular to the other two vector plane. In NumPy, to do the cross product, we simply call cross. So it's NumPy cross A, B, then that gives us the answer of doing the cross product on A and B. NumPy also gives us some very useful functions to create matrices with some certain properties. For example, we can create identity matrix by calling the NumPy I function. So the input is the shape of this matrix. So in this way, we can create an identity matrix with shape 4 by 4. With all this linear algebra information in mind, we can solve a linear system of equations using NumPy. So we have this A, matrix A, times B, times X equal to B. And let's represent it in NumPy. So we have NP array, then this first row, second row, third row, then B is a 1D vector, then it's a 4, 7, 3, it's 1D vector. Then let's check the length of this. The shape of first one is 3 by 3, shape of second one is 3, so it's a 1D. Then let's check the determinant of this matrix A before we do the inverse this matrix. To do that, we just call NumPy linear algebra parts, then it's and determinants for this vector is not 0, which means this matrix is invertible. So let's just do inversion of it. Then inverse A. To solve for x, we just use this inverse matrix and doing a dot product with the vector b, then we will have x. Dot b. NumPy gives us some functions that can solve these linear systems directly. For example, we can call a linear algebra solve to directly solve these linear systems. And it uses the method called Gaussian elimination Iterative Approach. And if you are interested in this approach, you can see it on Wikipedia for details. So let's try it. So it's NumPy linear algebra solve A, B. Sorry, should be small b. Then the function using NumPy's linear system solver is same as what we did here. The limitation of Gauss elimination is it's prone to round-off errors when we have a lot of equations. And if the coefficient matrix is sparse, elimination methods are very inefficient. And we can use some other methods like Gauss-Jordan elimination or LU decomposition to do this, to solve this linear system of equations. We can also have some iterative approach to solve linear systems equations. We are going to demonstrate that using Gauss-Seidel iterative approach. Let's consider a 3x3 matrix or a 3x3 linear system equation. Then we can arrange it to solve for x1, x2, and x3, and using this formula to update the x. So generally, we can update x using this equation. For example, if we have this system of equations, we can apply the Gauss-Seidel iterative approach to solve for it. Then it's an iterative approach, so we need to check for convergence. The convergence is checked by using this relative error, which is the error over the magnitude of this vector. If this error is smaller than some tolerance, then we stopped. There is one major drawback for the Gauss-Seidel method, is that it only works for diagonally dominant matrix, so it doesn't work for all the matrices. Here we provide the example function to perform Gauss-Seidel iterative method on solving a linear systems equations. Then we can try this first by solving a 3D matrix. So it's a matrix A. Then we also need to input the vector. In this case, it's vector B. And give it an initial guess. And we can also do it for 2D matrices. Then it's matrix 2, vector 2, and guess 2. Let's compute it. So it takes around 23 iterations to compute the first one, and it converged. Second case takes around 21 iterations, and all the error is pretty small. This is the end of our Python exercise tutorials. Thank you so much for your patience. If you have any suggestions or questions, please don't be hesitant to contact me. Thanks again. Bye bye.